where we left off? Okay. The reason I say we have our work cut out for us is we've missed a few days. Where do we need to pick up at? Oh. We have even more work than I thought we had. So one of the things that, thank you, by the way, one of the things that instructors are trying to deal with is how do I fit everything in? Okay.
We don't have to.
It ain't going to happen. So some instructors, hey, when I was your age, you know, when I was your age, you know, but like some instructors just to say, hey, we're not going to have time to cover this chapter. You guys go read about it. Tempting. I know. Yeah, but on to what we need to cover in Chapter 4. So we've been talking about humidity. We talked about 4 different ways you can describe, 4 or 6? 6 different ways you can talk about how much water vapor there is in the air. You're going to want to know that. And then we talked about if your goal is to get 100% relative humidity, it makes me feel oppressed just thinking about it. 100% relative humidity, your 2 options are to cool down the air, okay, and or make some more water vapor in that air at that temperature. So 100% relative humidity, we know, is got a lot of water vapor. One of the things you guys have been tracking is the day, if you've been doing your Monday through Friday, what the conditions of the atmosphere is percent relative humidity. And when you do that, actually, what you're doing is that number in the top there, I think we've talked about this, is what the environment really is. Okay, so the number on the top is the actual water vapor. The number in the bottom is a number from that one of those tables we looked at last week. So this is actual, okay, and this is from the table. So when we study weather, a lot of times we're kind of after the scenario to reach 100% relative humidity, okay? And again, how are you going to do that? Cool it down or add more water vapor. So I'm going to show you a second graph here, but this first graph doesn't have anything to do with humidity. This first graph is just basically, and I like to think of camping. If you're out camping and there are no clouds in the sky, there was no clouds in the sky while you were out enjoying your daytime, your maximum daytime temperatures are going to be, about 3 or 4 in the afternoon. That's what this is saying. Okay, and it's going to be coolest when you're going to wake up, about 6 a.m. So actually all this is looking at one day, what does the temperature do? Well, we said one way to increase humidity is to lower the temperature. So check this out. I should say percent relative humidity. One way to increase relative humidity is to cool down the temperature. So what this second graph is showing you the corresponding percent relative humidity. Haven't you, if you go camping, you get up in the morning, you're like, oh, I'm so clammy. I can feel the slime. And then you get up and you kind of dry off. Well, you are reaching, you're very humid conditions with those lower temperatures. Okay, the temperatures start to rise, the same amount of water vapor, okay, and because the warmer air can hold more water, your relative humidities decrease. Okay, so assuming that you still have the same amount of water vapor throughout the day, okay, at the warmest part of the day, I know it might feel uncomfortable, but the warmest part of the day, your percent relative humidity, how close you are to having the air saturated, is the lowest. Okay, so that's something to think about. You guys have, I think, a homework question on this. This might help with. Okay, so now I remember where we are. We hadn't even talked about this yet, have we? Okay, so relative percent humidity. This one is another way to say how much water vapor there is in the air. One of my, and I haven't, like, no one's patented it or anything, but a poor man's way of seeing how much water vapor there is in the air is to have, and these won't work, like Amy's got this cup with ice water in it because it's insulated. If the glass or the cup were not insulated, okay, and you're going to see a picture here in a minute, okay. If the glass isn't insulated, okay, what's going to happen is in the vicinity of that glass, you're cooling it down, you're cooling down the air, and if there's all sorts of water vapor particles, then they can go ahead, and they're almost near saturation anyway. When you cool it down a little bit, you can reach the dew point temperature, and it can go ahead and condense right there. Okay. One of the things, and I don't think any of you guys would believe it, but if you have a glass like this that is sweating on the outside, it's not because liquid has gone through the glass and now it appears on the outside. It's beating up. I just think that is so cool when I picture it. It's beating up on the outside because water vapor particles are liquefying right there. Isn't that cool? So back to my little device to see how humid it is. Okay, so if we have a cup of ice water there, not insulated, on one of our muggy summer days, okay, it's going to sweat. You go where there's a dry heat in Arizona, low water vapor, you have the same glass, which I don't know how you would do that, but a similar glass. Okay, if it's pretty dry air, has a really low dew point temperature, it's not going to sweat. Yeah, I'm just saying it's a poor man's way of testing the humidity in the air. Okay, so dew point temperatures. Dew point temperatures. You guys have been recording the dew point temperatures if you've been doing your weather logs Monday through Friday. Okay, dew point temperatures will always be below your current temperature. And so what this is saying is that depending upon how low the dew point temperature is, you kind of have a series of possibilities up here. If your dew point temperature is really cold, that means your air is pretty dry. Either that or you're already pretty cold anyway. Do you see like the negative temperatures again coming up? Oh my gosh. But check this out. If your dew point temperature, which is always lower than your current temperature, if your dew point temperature is like 75 degrees, you're like, dude, that is very oppressive. So, you know, you might be at 85 or 80 and your dew point temperature is 75. You know, it's very muggy, all sorts of water vapor, or high relative percent humidity anyway. So these look like isotherms. These look like lines that are connecting locations with the same temperature, sort of. They're connecting locations with the same dew point temperature. So again, the lower the dew point temperature, the meaning, remember dew point temperature is how far you needed to go in order to get 100% relative humidity. It means the air is pretty dry. I buy that, kind of desert sort of. Okay, these dew point temperatures here, you don't have to go so far to get 100% relative humidity. Now look to see if anybody's writing that down. Okay, the higher the dew point. Remember, dew point is a dew point temperature, and they are always below the current temperature. When would the dew point temperature be equal to the current temperature? When it's raining, exactly, when you're at 100% relative humidity. Yes. Yep. Did you need that one too? Okay. Now, here we go. This is where I thought we were. You know, as I was getting ready for thinking, how do you measure percent relative humidity? You know, I'm going to show you this way on a slide. I'm going to show you the Sling Psychrometer too. But there are like little gizmos that you can buy that just do it internally. And I'm not really sure how they work. I'll have to look into that because I've got one in the lab. But one way, if you like have hair that has a little bit of bounce to it, or maybe if your hair is straight, your hair does different things when the humidity is different outside. And actually, that can be used to turn into a device to measure humidity. So here is hair, and I don't think it has to be human hair. Maybe horse hair, I don't know. Okay. And depending upon how kinky the hair is or how kind of relaxed the hair is responding to the water vapor in the air. And depending upon that, that moves this. Okay. And you might recognize this drum sort of thing. We looked at those when we looked at how you take temperatures ongoing. This is just a drum that's rotating slowly but surely so you can kind of see what the humidity is throughout the day. So that's a hair hygrometer. The other one I want to show you is called a Sling Psychrometer. And I have, going to put you guys to work. Okay. I have enough for everybody. What? No. And I don't have enough for everybody. But, oops, sorry. Okay. So, Sling Psychrometers. They are very handy. They are very high-tech. Not, right? All you need for a Sling Psychrometer is two thermometers. Okay, and you see two thermometers there. And the thing that, before I kind of talk about the Sling Psychrometer, the thing that they're making use of is the fact that if there's a lot of water vapor already in the air, then evaporation doesn't want to occur. Okay, a pile of liquid water that's like minding its own business will not go ahead and evaporate if there's already a lot of water in the air. That's the first point. The second point is, I don't know if you guys remember this. I think we talked about it on that nasty day, so let me know if you need help filling in your notes. But when water goes from a liquid to a gas, okay, actually that takes energy. It makes sense. You boil water, right? It evaporates. Okay. So here's the deal. If you have evaporation going on, liquid to a gas, okay, where it takes energy, bottom line, okay? And honestly, what you're going to see here is, in a minute, is that during evaporation, actually, there's a cooling effect that the water will see. The water will see a cooling effect as heat is added or used to go ahead and evaporate it. Okay? So, I'll let you guys write those down. The next thing I need to do, this is just deionized water. Let me go on to the next slide. So this is a Sling Psychrometer. Your thermometers have two, You have two thermometers. One of them has a cute little sock. Isn't that adorable? And that's going to suck up the water. Okay? And the other one is, it'll get wet, but it won't stay wet. Okay? So you're going to dip both of them in the water here in a minute. Okay. So you need to dip yours in the water. I'll let you guys, you guys feel safe passing this? So dip yours in the water and then pass it back. It's just water, but I know you guys don't want to get your stuff wet. So the slide talked about ventilating your two thermometers, and you're going to ventilate your two thermometers by swinging it. Yeah. Sling, swing, sling, I don't know. Swings. So once you get it, once you dip it in, go ahead and sling it for maybe 10 seconds. Okay? And what's going to happen is the one that's wet, actually, evaporation will occur, and it will be cooled. Okay, the one that's wet. So don't be shy, swing around. And out in the factory, sometimes they use a, like a fan to blow them. You have to go like this. Just like a toy, just like a toy. Yeah. And we'll see if the one that has a sock is any cooler. Okay, so keep swinging if you're swinging. I'm going to start up here, and I'm going to ask for, in this order, what the dry thermometer says, and then what the wet, the one with that sock says. Are you still counting? Are you ready? Yeah.
Dry is 20.
20.
Sock is about 17.
I'll buy that. Thank you. Over here, Madison. Thank you. They're all going to be a little bit different. It could be a number of reasons. Okay. 22 and 14. You say change this to 15? Okay. Very good. Awesome.
20.
Very good. So did we have anybody there? 22 and 15? Kenny? Oh, wait a minute. Okay. 20 and 14? I kind of broke my pattern, didn't I, Kenny? 19 and 11? Wow. 22 and 12? Okay.
19 and 14.
19 and 14. Very good. Well, I'm liking this data. I am totally liking this. And for each one of these, we could come up with the difference. Isn't that, I just think that's neat that just the one with the wet sock is cooler. It's because liquid water is evaporating and it needs energy and it's zapping it from the thermal energy of the sock, basically. Okay? So we could come up with a difference, and actually we need the difference to come up with, use this table, to come up with what is the percent relative humidity in this room. I'm just going to do one difference, and I'm going to ballpark these as, what do you think, 21 maybe? And these as, they all look good, guys, maybe 14. 13? I'm going to go 14. Okay, so this would be our dry bulb. This is our wet bulb. So the difference is, what, 7? All right, let's see how we can use this table then. But do you see where the drier the air, the more the evaporation. The more the evaporation, the cooler that one is going that one with the sock is going to be. So the greater the difference in the dry and the wet bulb, then the higher the percent humidity. You say about 45. Let's see. So our dry one, we said go with, oh, these are even, aren't they? We'll go with 20. And then this is the wet bulb depression. So we decided, well, I'll stick with 7. 7. Where they intersect? Yep, I agree. Okay. See that? That's percent RH. Isn't that neat? High tech, high tech. Does that work for you? Very good. I'll go ahead and collect those so you don't have to worry about them. Thank you. Thank you. Woohoo! I have somebody who, and some of you probably might have done military time, and honestly, it's this sort of technique that they will do out in the field to know what sort of humidities that their troops are exposed to, so to know if there is a safety issue with regard to, I don't know. It's Monday. Okay. Thanks, Matt. All right. On to something a little different. Okay, so this is a review slide. Just to remind you, we are getting close to talking about clouds. I am so excited because I'm hoping that you guys remember the whole cloud thing is like liquid particles, okay? So we have air saturated, we have 100% relative humidity in our liquid clouds, okay? So here is the parcel of this is the parcel of air that we talked about earlier. Actually, it's identical. We talked about this when we talked about the 6 different ways to talk about water vapor in the air. And this talked about the mixing ratio and the absolute humidity. But my point is, and I want to emphasize this, is that parcel of air that goes up will, can you see getting bigger? And I love this, and I've seen this on a video before, that those weather balloons that we send up, you know, to get it fixed on the temperature, that environmental lapse rate, which we'll be talking about more today, environmental lapse rate. Those weather balloons get bigger and bigger, as big as a house, and then they bust. And Okay, so a chunk of air that's going up will get bigger. Okay, and you'll see these 5 sort of kind of points repeated in a slide coming up. But one of the things I want to try to convince you of is that the chunk of air that's going up and getting bigger is going to cool down. And what that has to do with reaching 100% relative humidity is what we were just talking about. If you can take a chunk of air and cool it down, you're going to get, that air will hold less and less water vapor. Cooling air down like we do, you know, as the temperature cools down at night, we reach 100% relative humidity. Okay?
How does it get bigger even if the temperature is
The way it gets bigger is, and we'll talk about 4 different reasons for making it rise in the first place. But the reason it gets bigger is that there's the air gets thinner up there. There's less and less pressure, so it's going to swell. Yeah. So, talking about chunks of air getting bigger, and chunks of air that are getting bigger cooling. I need to talk about kind of these 2 kind of things that go together, diabatic and adiabatic. I'm going to start with diabatic, but quite frankly, adiabatic is what we're going to talk about when we talk about chunks of air. Diabatic processes are what we do all the time when we cook. Okay, diabatic processes are basically, you have a system or whatever, it could be our pot that we want to cook something in, and we add heat to it. Okay, that's diabatic. Okay, this is to say that kind of as I've drawn my hands, energy can go back and forth. That's diabatic. Happens all the time. Okay, you take something, you take liquid water, and you want to make ice cubes, you put it in your freezer. Okay, again, diabatic. Okay, thermal energy is going to come out. Adiabatic is the opposite of that, in that your system, and kind of as I draw my hands around my chunk of air, or if I draw my hands around my pot that I want to cook something, maybe, okay. But adiabatic process is basically those boundaries with my system, okay, energy's not going to go in and energy's not going to go out. That's an adiabatic process. And this cooling that I'm talking, I just told you that a chunk of cloud, or a chunk of, it doesn't have to be cloud, a chunk of air that wants to rise is going to expand and cool. That's adiabatic. It all happens within that. It's just a smart little, I know it's not smart, but to me it's smart, okay? So adiabatic cooling of a chunk of air. I'll put all of these up. So this is just reinforcing what I've been saying the last few slides. Chunk of air. We'll talk about 4 reasons that a chunk of air would want to rise. But if you can get a chunk of air to rise and kind of think of an invisible boundary around it, okay, that chunk of air is going to expand, and expansion is work, and work's got to be paid, and it's paid for at the expense of the thermal energy, those cute little particles that are in that chunk of, you know, that parcel of air. I know, it's just, they all work together, okay? So chunks of air that are rising will expand and cool. And it's adiabatic because no energy goes in or no energy goes out. It's all within that chunk of air. Okay, so I told you that we were going to revisit the weather balloon, the environmental lapse rate. We are going to revisit that. But before we do that, I need to talk about something called the dry adiabatic rate, or the DAR. And it's so important, I'm going to put it on the board. Don't you just love the little acronyms? Dry adiabatic rate. Does anybody remember what the environmental lapse rate is? 6.5, exactly. 6.5 degrees Celsius is a cooling temperature for every 1 kilometer you rise. But that's real ballpark. And we have to, it'll change, you know, time of day and location and all that. But the dry adiabatic rate, DAR, you might want to make sure that's on your note card, okay, is a cooling of 10 degrees Celsius per every, and you can either say 1,000 meters or 1 kilometer, same thing. Okay, right. So it's kind of fun. So I like what your author does. Okay, we have several figures here where we talk about a chunk of air that's rising. This happens to be a chunk of air that's 32. Okay, And each line there is 1,000 meters. Each line is 1 kilometer. So I know it's math, but we can do this. Okay, so cooling from 32 to 22, right? Cooling from 22 to 12. Cooling from 12 to 2. Okay, we good with that? The dry adiabatic rate of cooling. It's kind of fun. Well, sometimes there are times when I'm going to talk about 4 ways that you can take a chunk of air and do this. 4 ways you can get it started moving up. But sometimes in our atmosphere, we take chunks of air, and chunks of air are forced downward. And as they're forced downward, the air gets thicker or more pressure. And there's more pressure, it contracts. And as it contracts, it doesn't do work, but contraction work is done on that chunk of air, so it heats up. Okay, so actually, see the red arrows? I'm glad the lid's on this. The red arrows is if you were to get this chunk of air to go down, for instance, if it was at 2 degrees and if you were to be able to kind of force it down 1,000 meters, it would warm to 12. Okay, and then force it down another kilometer, it would warm to 22. Okay, so chunks of air that do like that do get warm. Case in point, and it might be a little while before we get here, but on your weather maps, we talked about the L's are lows, low pressures, the H's are highs, high pressures. There are times when that big old H, that high pressure we see, actually is because of this. Air has been forced downward and created a high pressure. High pressures oftentimes bring really clear skies, but really warm conditions. So, all right. All right. Oh, I love this concept. Lifting condensation level. Isn't that just have a ring to it? Okay. So, you know what's going to happen is we're going to kind of combine the fact that a chunk of air as it rises will cool 10 degrees Celsius for every 1,000 meters it rises. We're going to combine that cooling effect with reaching the dew point temperature. Cooling effect, reaching the dew point temperature. Cooling effect is basically that chunk of air becomes saturated, 100% relative humidity. And when it becomes 100% relative humidity, then you can go ahead and it'll turn milky white, and you'll get your clouds. And the elevation at which that happens, that elevation is called the lifting condensation, because water is going from a vapor to a liquid level. Lifting condensation level. It's so pretty. Okay. All right. So if there's a dry adiabatic rate, there needs to be, and I need to talk you through, a situation in which it's called a wet adiabatic rate. As the word wet implies, it's got water's doing something, and it is. If you have a chunk of air, and within that chunk of air, if you have condensation going on, if you have milky white clouds forming, gas going from a gas to a liquid, okay, actually, instead of requiring energy, energy is going to be released. And so that chunk of air might rise, but now it's going to rise at it's going to cool. It might rise and continue to cool, but its cooling rate is going to be diminished. So instead of 10 degrees Celsius, as it rises, cooling, it's only going to be 5 degrees. Okay? So the wet adiabatic rate occurs when you have condensation going on. And I like what your author's done. And you're going to see, you can tell it in his pictures because you'll see the milky white. And then you know to apply this rate of cooling. Okay, wet adiabatic rate is less than the dry adiabatic rate. And it's going to cool at 5 degrees Celsius for every 1,000 meters that you make that chunk of air go up. Now, at the end of this chapter, in my notes, I try to clarify, but your author actually switches from having a rate of 5 for the wet adiabatic rate to a rate of 6. I don't know why he did that. But don't blame me, and I'll try to make it just fine. Okay, so let's look at an example of that. Okay, cool. So that looks like normal. You see how that goes? It's kind of piggybacking on what we looked at before. You got a chunk of air, minding its own business, and it's going to rise. And it starts out at 32. The white line is 1,000 meters. It's going to go from 32 to 22. Then it's going from 22 to 12. And it's going from 12 to 2. Now, and I think it's called, right at, do you see where I would say 3,000 meters is the lifting condensation level? I know it says condensation level, but put LCL there. That is your LCL. That's supposed to be an L. Okay. The reason is on this figure you can see condensation occurring. All right. Now we switch gears. When condensation is occurring, check this out. Now you need to apply this rate. So it's going to cool from 5 to what? -3. Okay? Condensation is still going on. It's going to cool from -3 to -8. You buy that? I do. Not too bad. Well, how do we get those chunks of air to go up? These are the 4 ways. Okay? Why would a chunk of air want to do that in the first place? Well, here are 4 ways, and they're kind of, and they'll be on your test in some ways, because it's important. How do you get a chunk of air to go up? Okay. The first one involves mountains. The second one involves air masses and fronts. I'll just kind of talk you through them. Orographic lifting. I bet you're going to be fine with this. Actually, orographic lifting, a means of getting a chunk of air up, is something you see the windward and the leeward side. We talked about those terms in the last unit of material. Basically, a chunk of air is slammed against the mountain, well, because of a prevailing wind, maybe, and it can't go through the mountain, not according to quantum mechanics, but it has to go up and over the mountain. As it's going up, it will expand and it can cool. Okay, it can cool to the dew point temperature. Okay. This is kind of neat because on the previous slide it talks about the leeward side of the mountain, and these are actually on our west coast mountain range. So this would be the Pacific Ocean. Here's your orographic lifting. Okay, it can go ahead and cool to the point of dumping its precipitation. Okay, and then that chunk of air will continue to go downwind with the go east with the prevailing wind. Okay, and then over here it's basically cried itself out, so it's pretty darn dry. Not to mention if you get any sort of descending air, it's going to get nice and toasty. Desert? Sound like a good place for a desert? Yeah. Rain shadow side because of the lifting that occurred on the windward side. Okay. Frontal wedging. Sorry, I just giggle every time I see wedging. We're going to talk more about air masses, okay, and weather fronts. But basically, I think we talked a little bit about it before. But an air mass is awesome. I mean, it's like as big as a couple of states. A chunk of air that goes marching this way or that way, depending upon. And the reason it's an air mass is it sat in one spot for a long time. Sat in a very cold spot and then decided to move, or sat in a very warm spot, decided to move, sat in a very dry, very wet spot. But you have this chunk of air, A, and you have chunk of air, B, and where they meet is called a front. Okay? And I think we talked about this before, whether the cold air is on the move pushing in or whether the warm air is on the move pushing in gives us our cold front and warm front respectively. So cold front just means that the cold air mass is pushing. Warm front means the warm air mass is pushing. So the way this gives us lifting, and notice that I don't necessarily say which one's being the aggressor. The warm air, see the warm chunk of air, see the cold chunk of air, where they meet, that's the weather front. But I'll just leave it this way, that you've probably heard warm air rises. Yeah. Warm air is less dense, it's fluffy, it's buoyant, it wants to rise. Cold air is more dense, it's like. So actually, regardless of which one's being the aggressor, when a cold air chunk of air meets a warm chunk of air, this one's nice and dense, and this one's fluffy. Okay, so we can definitely get this warm air lifting up, and that is your lifting, frontal lifting mechanism. Okay, and we'll talk more about that. There's definitely more to be said about that. Convergence. It seems like I used this analogy in here before, but convergence means, I like to think of being on a playground with a bunch of like, first through fifth graders and having a bag of candy, okay, and somehow all of a sudden throwing it over there. So convergence is basically all those little kids going for the candy at the same time. And pile up, right? So one thing about that, and the little kids couldn't do this, but when air converges, where it converges is a lifting mechanism. Okay, it'll go like that. So converging air. And then the last one, actually you've seen before. How do you get a chunk of air to rise? Okay, so this one, you might have seen this one when we were talking about albedo, about basically there are certain colors or maybe textures on the earth that suck thermal energy more, are less reflective, a lower albedo than other places. And so that's kind of what's being shown here. Like one of these spots is not like the others. It gets warmer from the sun, and as it gets warmer, it heats the air around it. So this convection, or localized convection, is a way for a chunk of air to want to rise. Why is it rising? Simply because it is warmer. It's fluffier. It's less dense than its surroundings. Okay, convective lifting. And those kind of thermals or convective lifting are often, our birds, our raptors, enjoy soaring, catching those. Okay, as much as I want to go on, I think that's a good place to stop. So we got a chunk to, we'll knock out this chapter for sure on Wednesday. On what? Thank you, ma'am.
We only have to do one of those papers.
One of these?
No, one of the papers.
No, you only have to, like, there's a project requirement, and this satisfies the project requirement.
No, but I'm saying you said we could do those papers.
You can do.
Extra.
Yeah, but it only goes towards quizzes and assignments. But, like, if you missed any points on assignments, then if you do because since you already did this, if you do a report, then your extra project, which could be a report, will count towards your missed assignments. Did that even make sense?
Well, my thing is I like to fail that test, so I'm trying to use it.
And I'm just trying to let you know that it doesn't help test points.
Well, not test points, but
Yeah, and I have to double check, are you missing any points in assignments or quizzes? Because if you're not,
maybe quizzes.
then it would.
I know I missed an assignment, but I came to the
review session.
So I think that's the only assignments that I was missing.
Okay.
Because I started working.
Yeah, I just don't want you to do extra points that that's going to help your. Thank you, sir.
But we
All
get
right.
to do 2 of these, right?
Yes. That looks good, Joan. Very nice.
Because, yeah, I was just wanting to do.
Yeah, I just want you to. It's
Not my exam grade, I just need my grade.
yeah, and it depends on examples. If you missed any points in your assignment quizzes, then it'll help.
Okay. But we
Review
still have to
session.
do the picture project.
Nope. This is it.
Oh.
Yeah, I know. There's like 5 different things you can do, 4 different, and you only have to do one.
I looked over your Scantron.